I'm Matt Godbolt.
And I'm Ben Rady.
And this is Two's Complement, a programming podcast. Hey Ben.
Hey Matt.
How you doing?
I'm doing great.
Awesome. Well, I've been thinking a lot about performance recently. It's not something I've been worrying about for a while. I've been doing more functional stuff, but now we're sort of trying to think about how best to measure, track, and improve the performance of code I'm working on. And I wondered, we should just talk about it because, frankly, that's all we do on this podcast is just talk about the things we're doing in our day job in some way or other, or allude to them.
Thinking about the exact same thing, actually. So this is good. This is good. Yeah, make it right and then make it fast. Well, the make it fast part.
Right.
You gotta measure it, right?
Measure. Well, I think that's the key thing. I think I think if there's, and I think we've mentioned this before. One of the key things is always measure. Never trust your instincts, because no matter how many years you've been doing this, and I've been doing this for nearly 3 decades on and off, you're always wrong. And even when you account for the fact that you know that you're always wrong, you're like, well, I know I'm always wrong, so it won't be A, it must be the B thing, and then you measure it and it's some other thing. All right, I think I've got a presentation. I don't know, is this on my YouTube? I don't know. But there's a presentation I give when I go around to universities when we're trying to encourage graduates, new graduate folks to apply. And I do a deep dive on a C++ optimization problem, and I set it up. And the funny thing is, I set it up for myself, thinking, haha, everyone will expect A, but it will be B. And then I ran it, and of course, it was neither of those things. It was something I'd never even heard of, suddenly rearing its head. I'm like, this is amazing. This is exactly what I want to do. So that's what the presentation is about. And so always measure. I think we all know that. And profiling is one thing, but how do we? What's your general approach to performance?
I mean, so I think we hit on this a little bit already, but I think you got to really start with the basics, which is, don't be superstitious, right?
What do you mean by that? I mean, I'd say that's intriguing, right?
I mean, the superstitions. There's so many of them. You hear them all the time. It's like, oh, you can't use this structure or this call or this function because it's too slow, right? That's kind of stuff, right? And it's like, all of that stuff is sometimes it's true, but it's always context dependent. So it's like, if it was true, it was only because you got lucky, right? And it's like A is slower than B. Well, there's a 50% chance you're right. That sort of thing, right?
Right.
So don't be superstitious, right? And part of that, and so I think part of the reason people fall into that trap is they're like, well, but if I don't learn what things are good, what things are fast, what things are slow, which things are memory efficient, which things aren't. If I don't learn these things, how am I going to write any code without performance testing every single line of it as I write it, right?
Right.
And I think that is where you get the very old, graybeard programmer wisdom of first make it right and then make it fast, because the first thing in measuring is figuring out which parts of the code actually matter, because a lot of them just don't, right?
That's true.
If you're doing sort of superstitious memory tricks in your command line parsing, arg parsing, it doesn't matter.
I'm with
right?
you. That's now I get what you mean by that.
Yeah.
I would, to sort of take the other side of that just a little bit, right? There are some things that are, in particular in C++, that you could do quote unquote wrong forever, and it doesn't really matter. But if you've written an entire application where you've passed everything as a string by value or whatever, that you profile it and it's like, why is my application slow? It's not slow anywhere in particular, it's just slow everywhere, because you've done something that's kind of harmed you in the approach you've taken, and it can be hard to unpick that after the effect, even if it's right.
Right, absolutely. So in those cases, I think the key there is you still need to measure. And something that I do a lot with these kinds of things, this is a classic example of this. Let's say that you have, I'm going to just pick on Java for a minute. Let's say that
other languages are available for picking
other
on.
Languages are, and this technique would work in any of those languages. But let's say that you've got some data structure in the JDK that you want to consider using, some list implementation or something like that, and you're like, I want to go and write my own version of this instead of using the JDK one because my own version will be faster, right? Let's just say that you want to make that claim.
We've all made that mistake before now. Right. X is slow, I'll just write my own, and then very quickly you discover, it's harder than I thought, or whatever.
Yes,
but
yes.
Sorry, continue.
So if you're going to make that very bold claim, right, I would submit that what you need to do is build a performance test that shows the performance of the built-in thing, the performance of your new fancy thing. At the most basic level, make sure that like when you run that once, you're actually correct that it is faster in that context, but also keep that around and have it part of your pipeline so that as you in again, case of Java, upgrade your JDK or run on a different architecture or change some Java heap setting or whatever it is, that holds true in all situations. Because guess what? The guys that wrote the JDK thought a lot about all of those different situations, and you maybe have not, right?
Right. Yeah. So writing those tests, though, that's probably the real difficult thing, right?
Yes,
in my experience,
it is difficult.
I mean, if we're picking, you picked Java. Java has some extra fun and games on top of like what I would normally worry about when I'm writing benchmarks or similar tests that are trying to do performance. In as much as the JVM and the JIT are going to come along and like optimize and give you even more of a hard time than like your equivalent in other compiled languages. Although they have their own problems too, right? Like, and the number of times that one's written a benchmark around a C++ thing only to discover that because you passed in constant values to your tests, the compiler has just gone, you know what, right. The answer's 12, we're done here. There's no code runs at all, right?
Yep.
So there are definitely challenges in this. So
Yes, definitely.
How does micro benchmarks are great at showing very specific cases, but they're often not necessarily very representative of your program at large. There are macro effects sometimes, especially if you're like, I can be more cache size efficient with my implementation, then you might discover that actually that all goes out the window when you're actually running in a program where someone's mem copying 2 gig of data around before they call your function or whatever. There's a lot of things to think about. So how do you even go about writing that apparently straightforward, write the test of my list versus the
right.
JDK
Well, no,
list.
it's not straightforward, and that was sort of my point. Is that if you get the easy stuff out of the way, don't be superstitious, right? Like measure these things. Don't assume that you're super smarter than all the people that wrote the standard library, right? Like don't do that. But like now, if you get all the easy stuff out of the way, now you're to the actual hard part,
the meat of the problem.
With the meat of the problem, which is, okay, you're going to write the benchmark that shows that your super fancy list implementation is faster. How do you do it in a way that's really real, right?
Fair as well, because like, it's like, hey, I tested it and it's faster. Good. Don't worry about it. What happens if you pass null values? Oh yeah, don't worry about that. Right. Some special cases thing.
Right. So to me, that is the tricky problem, right? One of the things that I was just sort of, we were talking about this, I think a month or so ago, so I was kind of wondering, it's like, I wonder if you could use, and this is of course on brand for me, but it's like, I wonder if you could use some of the generative testing frameworks to generate, because you're just talking about like, null values, constant values, stuff like that. And you can also generate random data, right? But I was kind of wondering, it's like, generative testing frameworks have these things where it's like you define a function that has like, can create a range of properties, can create different types for you. And it's like, you can handle all that stuff yourself. But maybe you could use some of those to generate some data for performance testing that wouldn't be totally bonkers. I don't know.
I mean, I've written stuff before for like maps when we've been doing stuff for the market data. There's a lot of map accesses in the finest world of adding and removing and looking things up by giant 64-bit keys. And if you're trying to do things fast, there's 100 different ways you can skin that. And I've ended up generating effectively add, modify, remove loops in the generative thing, and they have to balance, that for every add there must be a remove at some point, but there could be some modifiers in between. So you write this sort of, as you say, generative approach, and you're like, okay, here's 100,000 operations that I'm going to stream through, and I can randomize them with a seed so that I know they're going to be the same each time to be somewhat fair, and then I can run it through map choice 1, map choice 2, map choice 3, and get some idea that it's representative. And maybe you could even measure your actual workload and say, typically we have more modifiers than we have anything else, or maybe have adds and removes, or get some kind of smell about the data that tells you that it looks representative. But to your point, generative stuff. And if it's not as complicated and path dependency as a long-lived map where you're adding and removing, if it's just, like, hey, I've written my own square root routine, then of course, then you can throw random numbers at it, or you can throw ascending numbers at it, or you can throw all those things at it, I suppose. But so that sort of covers some of the tricks and problems of like generating representative data.
Yeah, I haven't actually tried. I have to put a disclaimer out there, though. I haven't actually I haven't gone and gotten a generative testing framework and like plugged it into a performance test. And
give me the name of one of them. I'm forgetting. There's
there's QuickCheck, which is the original one, and then there's all the QuickCheck derivatives.
Sure, it was just QuickCheck would be enough for me to remember like the kind of thing. I knew that's what I was thinking of. I couldn't.
Right. Yeah. I'm trying to remember some of the specific names, but they're all a lot of them are QuickCheck derivatives. So it's like probably JCheck in Java.
I imagine. So,
PyCheck in
C++ check or something somewhere. Right. I'm sure it rings a bell anyway.
Yeah.
No, that's cool. So that kind of somewhat covers that. I'm sure it's a huge topic, and you and I have got a little of experience in this, but maybe not as much. But then the thing that immediately springs to mind when I'm doing these kinds of performance things, particularly in my world where I have the luxury of knowing what kind of computer system I'm going to be deploying my code onto. In fact, sometimes I get to choose what system it is. I get to pick the CPU and how much cache and all that kind of stuff. But my development workstation may not be the same as that. And my development workstation is running 1,000 other processes, all the Javas in the world for all my IDEs, my music player. It's got Chrome and 300 tabs open, and that's taking all the CPU in the world for reasons I don't know. Or I'm in a video conference with somebody and
so you're mining cryptocurrency somewhere.
Something like that.
Yeah.
So
or
there's
a web page that you're visiting is mining cryptocurrency.
Oh, more likely as it happens. Yeah.
Yes.
And so obviously it's not necessarily representative, and certainly another sort of key piece of advice when people talk to me about like performance testing, other than measure everything, is measure what on a system that is actually representative of where you're going to be running your code, because it's so easy to sit there and kind of go, oh, I picked this map, it's perfect, it does the work really well, and then you discover that it works fine on your system, but with 4 times as much cache in 3 NUMA nodes or whatever. 3 NUMA nodes? I don't know. 4 NUMA nodes. Come on, I don't know what's up with me. That
powers
suddenly,
of 2 only, please.
Powers of 2. Yeah, exactly.
Yes.
That it doesn't work as well, or something else is more efficient because of it. And obviously, this is very micro optimization based, and many people won't ever be worrying about this in general. But it's something to be aware of, right? Yeah. We've all run something and gone, oh, that seems a lot slower, and then you run it again, you're like, oh, it's back to normal. That's fine. And sometimes that's an interesting thing to know, because you're like, well, why is it so variable? Another one is like, well, yeah, I was mining cryptocurrency at the same time, or something else happened in my computer.
Yes.
So, what all can one do to help in that regard? Do you think?
Oh man, I mean, I think a lot of this ties into how frequently you measure and check these things. What you want to do, I feel like, is you have it as part of your regular continuous deployment pipeline, right? Like every time I make a change to the code, I want to run the unit test to make sure that the behavior is correct, and I would want to run some kind of performance test to make sure the performance hasn't changed. But that second part is way harder than, when I call my square root function, does it give me the right result, right? So it's really tricky. I honestly can say, like, I know some ways to do this that don't work, but I don't really have a lot of ways to do this that I'm like, yes, this is the way you do it, right?
Right.
Any sort of test where you are using time, where you're like, oh, well, this amount of things should run in 10 seconds or less, you're scheduling pain in the butt brittle test debugging.
We've all
for the future,
seen this shouldn't take more than 10 seconds timeout on a shared build server that's running in 3 layers of Docker and 12 different hypervisors or whatever.
Right. So like those things, maybe someone somewhere can say that works for them. It has never worked for me. And I every once in a while I'll try it again just to make sure that the world
it still doesn't work.
And it still doesn't work.
The world has not moved on.
Yeah. So there's that. I haven't really looked at sort of other ways to measure, performance, like something, we were talking about the other day, is like, measuring like instructions, like how many instructions did this take the last time I ran it? How many is it taking now? And maybe why is it different?
Yes.
But I've never actually done that. So I don't know.
I have a friend who uses that approach at least as at least a starting point. I mean, there are some simulators that you can get that you can run your code through that will give you like a fairly decent approximation, as well as actually measuring the instructions. Obviously, if you measure the actual instructions, then you've got some amount of noise from the measurement system itself. But if you're using like effectively an emulator to cycle level run through your program, and it's fast enough to actually run, you can say, well, how many instructions did it get processed? How many times did you access the cache? That kind of thing. Now, again, that simulation may not represent reality, but it's something that is measurable and deterministic, and that is kind of a good thing to have. So that's an option.
Yeah.
Another thing that I've done in this world is had a special build agent that runs on just that one machine that's only there to service your request, or it runs at 3 a.m. and you're like pretty much guaranteed that nothing else is running on that agent. And rather than erroring on it, you just graph it. And that does require human persistence to kind of look over and say, oh, wait a second, when did that spike up, right? And, you know, maybe you could use some kind of anomaly detection type stuff to say, hey, the last 4 readings have been within this band, and suddenly it's outside of it, in both directions, right? You know, sometimes the too good to be true error is worth it. Like, hey, suddenly this went faster. What happened? Oh, we upgraded the compiler. Oh, right, now it's just not. It's the compiler's too smart for us now. It's not actually testing anything useful anymore.
It's not testing anything useful anymore. So I almost wonder if some of the, and you know, we've definitely been dealing with some of these things that work, is sort of like the comparing one test run to another, and looking for, you know, like deviation, right?
Right.
So it's like, you know, manually looking at it in a graph is one thing, but if you want to get some amount of automation around it, like I can imagine like a continuous deployment pipeline where it's like if the performance characteristics of this are radically different, it doesn't just automatically go to production. Someone actually has to go and bless it and be like, okay, yeah,
this is fine.
Like, this is fine. Like, we understand that it's going to be 10 times slower, or like you say, 10 times faster, right? Because maybe
hopefully the latter,
your metrics
for good reason. Yeah, not for the bad reason.
We were expecting it to be 10 times faster. We did other tests to confirm, and it was great, awesome.
Yeah. I guess the other thing about like graphing that I sort of implied in this as well is that the noise level you can sustain higher levels of noise in a graphing based thing, because you're naturally going to say, well, it took 0.7 seconds on average to do this thing. Now it's gone to 0.78. Now it's down to 0.69, and it kind of fluctuates around, and you can kind of squint and look at it and kind of go, well, this is within what we'd expect. And maybe every now and then there's an anomaly, and like rerun it. I know it's not a great answer. It's very manual, it's very labor intensive, but it allows you to see a trend more so than have some kind of type bound that you set and say, well, it just should definitely take no more than 0.9 seconds to do this operation, whatever that is.
How much overlap have you found between the tools that you would use to like automatically check these things and the like actual, like, you know, crack open the toolbox, get the wrench, get the screwdriver out for like doing the optimization, right?
Interesting.
Because I think there's some areas where they overlap, but there's definitely some areas where they wouldn't.
Yeah, there's the first thing that springs to mind is a lot of the tools that one would use that are very, like, as you say, specific to like, tools that you get out of the toolbox. You know, count the number of CPU instructions retired, count the branch prediction mismatches and things like that. Those do require a system where you have access to those things, and there are normally layers of Dockerisms and virtualization that prevent you from actually accessing the damn CPU's functionality, because you're sharing it not just with other C processes on your operating system, but actual other operating systems probably on your build agent, compared to I'm at my keyboard on my actual computer and I've got the freedom of sudo installing and like monkeying with stuff. So there's a sort of practical issue there, but that's not necessarily problematic. You can configure these things. It's just I've often had to badger various folks who are involved in the virtualization. Can you enable this, please? I need it.
Yeah.
But that aside, I mean, first of all, obviously the cycle counting thing that we just talked about, where you simulate it, that obviously is a tool in the arsenal of things that you have available for you. That is amenable to being scripted and run, albeit slowly on a CI. So that's one thing. And then if you have got something like Perf and it does work, then you can run some things and you could sort of count the number of, again, broad phase stuff, like branch prediction mismatches, and you could run it over a representative like run of your program rather than targeted tests, and kind of at least have some heuristics. Again, they could maybe graph them, so I guess you could use them. But then once you get down into the minutia, it doesn't necessarily, nothing springs to mind as what you could extract, because I don't know, the thing about these tools when I use them is like it's a journey into the unknown. It's an exploration into the literal unknown. And again, like like the presentation I give where I'm like, where on earth are we spending all of our time in this simple function? And it's like, oh, it's in the locale system in C++. You're like, I didn't even know there was one. How did this happen? Where are we? Why are we here? You know, like, and so trying to sort of like capture that in an automated way doesn't necessarily spring to mind. But obviously the metrics you can get out might be the same ones that...
I think it's the difference between detecting that there's a problem and then figuring out what the actual problem is. And those are two... Sometimes there's overlap between those two things, and it can make tooling simpler to use. But for the most part, I feel like they're very separate activities.
Right. There are some. I mean, again, the broad phase stuff. So the top level stuff. If I'm literally just going to do perf stat on a thing and just get back like the things that get back by default, which is how many CPUs, how many CPU instructions were retired, how many were issued. There's about a half dozen stats and some things that are inferred from it, and that kind of gives you some idea about it. There's also an approach that I think Intel first gave out, and this is very Intel-centric again for folks who are listening and that are maybe not so au fait, but like CPUs in general have multiple like stages in them, and there's a sort of front end stage which does fetching of the instructions that need to be done, which is executed, which is branch prediction feeds into that, and all the badness of inaccurate branch miss prediction, I suppose. There's the reading of the bytes that are actually the instructions, which is cache and memory. There's the decoding of the instructions and turning them into the actual thing that the CPU can execute, because nothing really executes the bytes directly anymore. So that's the front end. Once those things have come out, they go into like a box of things that I know I need to do, and then there's some out of order magical stuff that happens, and then like maybe you've got only one divider on your chip, and now you've done lots of divides, and now you've got like contention on divides. That's sort of in the back end, and then there's retirement where it's like now at the end of the day all the instructions have to come out. So there's this approach that you can kind of hierarchically zoom in on the bit that's actually the bottleneck. And so the first couple of levels of that might be something you could run automatically and note when something changes. Like, hey, this code ran before and it was absolutely limited by the front end. We couldn't get instructions out of memory into the CPU fast enough to sustain the whatever workload you gave it. But hey, now it's suddenly switched, and now suddenly you're bottlenecked somewhere else. And that's an event you can say. And I don't know why or what, but I can perhaps flag that up as being something that happened. I don't know how feasible that is to actually do automatically, but it strikes me as something like if someone handed me a product that did that, I'd be like, yeah, I guess I'd use that. Just run it on my little test case and see. But yeah, I don't know. It's a fun thing.
Yeah. What about like visualization? Like I know that we've used a few different kinds of tools for like visualizing like flame graphs, and like I always get the tree of calls, right, that you can click down and sort of see.
I think
what things
was
have
it
you used.
Brendan
Like,
Gregg's
what tools have you used for that?
flame graph thing is just like one of the best visualizations. But then if you've ever brought up Chrome and like done a recording in Chrome, like JavaScript thing, Google's viewer that shows like a timeline and gives you sort of a combination of both the flame view and also this is what things were happening on what threads when, which is great for debugging web pages. But you can actually record this stuff and convert like system level traces either on your Android phone, or if you use your own stuff, you can output the format. It's pretty straightforward, and then you can load it and visualize it in that. So that's been a really, really helpful thing. They've recently spun that out, or I say recently, I don't know when they did it, but I noticed recently that they used to embed the viewer separately in, I think it was in the Android project originally, but now it's been spun out of its own thing. And so at perfetto.dev, you can go and see the web-based browser. You can load traces into that. It's pretty cool. And I think, the thing that we were talking about before we started recording this was that there are a number of tools that are now starting to target Perfetto traces so that you can load them and visualize them in that. And one of them was, I think, Jane Street released something where they were using like the new Intel tracing stuff. we should really have done more reading about this beforehand. But like I've seen a couple of things recently which have targeted this, and certainly the newer things that are coming in the most recent revisions of Intel chips are allowing more and more fine-grained, accurate, and low overhead ways of tracing what the heck is going on in your program, which is super awesome. Normally the one finds oneself compromising and saying, I have to just keep running my program over and over again, and I'm doing some kind of like sample-based profiling, and that's okay for getting, there's a lot of branch mispredictions, and I can sort of vaguely see the area of the code where they're happening. But if you really want to know, like, in what iteration of what loop something happened, you need to have this new branch tracing, and I can't think what the other new thing is now, which is terrible, but there are some new things in the chip. And effectively, there's a highly compressed buffer that the CPU is streaming out. This is what I did to, which is the coolest thing, right? I mean,
like
I used
journal,
to have
basically?
a journal, but I used to have this on the PlayStation 2, right? There was this crazy. We're running out of time, unfortunately, because we maybe have to talk about this another time. But there was like this crazy piece of hardware that was like a 4 times bigger PlayStation 2 dev kit, which were already much bigger than like a PlayStation 2 ever was. And I used to use it as a footrest mainly because it was the right height, and it was worth tens of thousands of dollars. But it had a foot switch, and you could play your game, and you could hit the foot switch, and it was in a ring buffer keeping 16 megs worth of this kind of trace information for all the different components over the whole PS2. And one of the cool things was that, you go like, why is it taking so long? You could see the graphics being drawn. You could then see, because effectively the CPU only needs to tell you when it took a conditional branch and which way it went. Because the rest of the time, if you know where it is, you can say, well, I know what a CPU does. It follows one instruction after another. The only time I need to know what happened is when it says, I took the branch or I didn't take the branch, and I can reconstitute the flow then, provided I know which CPU cycle it was. And then everything else is like, I branch mispredicted, and you're like, that's great. Okay, that's an event that goes into the journal. Yeah, lots of fun. Anyway. Yes. What were we talking about? Visualization tools.
Visualization for photo. By the way, Magic Trace, I believe, is the name of that Jane Street thing, and that is on
awesome.
The Jane Street GitHub account.
I should find the other thing that Travis Downs tweeted about the other day, which I was super excited about, but not apparently excited about enough to remember the name of, which was to use the same kind of techniques, I believe, that are now available in these newer CPUs to do effectively a cycle-by-cycle simulation of a piece of code by running it over and over and over and over again and saying, hey, stop after 1 cycle and tell me what the counters look like. Stop after 2 cycles and tell me what the counters look like. So you can kind of like slowly run the same bit of code over and over again and kind of say, well, now measure this, now measure that, now measure that. A lot of the problems come from the fact that the CPU has many, 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 many counters that are available, like for events, interesting things that happen, but they can only count like 3 or 4 of them at a time. And so you have to keep being able to rerun the same piece of code over and over again.
That's very interesting.
Anyway, we're actually running out of time. I can't believe this. I've gotten excited again. About something. I mean, it's uncharacteristic of either of us to be excited about topics.
To be so animated about all of these things, but yes.
But we should try this and talk more about this some other time. There's so much to think about.
Yeah, maybe there's a part 2 here. Maybe
there could be a part 2. Let's think about that.
We should think about that.
So, cool. Listener, if there's a part 2, there will be a part 2 after this. But maybe this is the whole thing. I don't know. Maybe we've actually peaked.
Yep, that sounds about right.
All right, well, I guess until next time, my friend.
Until next time.
You've been listening to Two's Complement, a programming podcast by Ben Rady and Matt Godbolt. Find the show transcript and notes at twoscomplement.org. Contact us on Twitter at 2CP, that's at TWOSCP. Theme music by Inverse Phase, inversephase.com.